Okay. Okay, so today we will be talking about data storytelling and how data storytelling can help us in um, addressing data analysis problems. And we will do this with the science of data analysis and the art of data analysis. So I'll begin with a quote from Halvarian, a chief economist at Google. He said, the ability to take data, to be able to understand it, to process it, to extract value from it, and to visualize it, and also to communicate it. That's going to be one of the hugely important skills in the next decades to come. And that's one thing that I wanted to pass to you. So if you have these skills, this is going to be like a huge important skill to have in the next decades to come. So in my analysis stuff that I've done so far, I've realized that these 5 key steps helps in driving value from your data. That is data, information, insight, decision, and actions. It starts with collecting your raw data, and that would serve as the foundation for gaining knowledge on a subject. And then the data is organized and summarized in reports, turning this raw data into information that's easier for some people to consume. And then when these people examine these analysis and these reports, they discover meaningful insights, and that inform them to make decisions and then to take actions, which in turn helps them create value out of that data set that you have. But one thing that we should know is if you are trying to have these reports for people to create value out of these, we need to strive to communicate our information and not just to inform. Okay, so here is also another quote from Andrew Grove. He's an American businessman. He said, how well you are able to communicate is determined not by how well we say things, but by how well we are understood by our audience. Okay, so something that I wanted to show you with this picture here is that when you inform someone, you are simply disseminating the data in a passive clinical manner. You expect your audience to interpret and comprehend the data themselves. If you have any overt messages that would not be conveyed to this audience, and or any interpretations of the data will not be passed on to the audience, it's just the fact of what is happening in the data set. So, but on the other hand, when we communicate, we just clarify what the data means. And when you communicate, you become an active, disseminable participant in the delivery of the information, rather than just being a removed, neutral person, and when you are just simply informing your audience. So when your goal is to get through to your audience, you must engage them by communicating in a way that guides them through the numbers and motivates them to act. And storytelling is critical to effective communication. When you want to communicate your data to people, you need to have a storytelling and not just informing them to communicate to them. Okay, so why do we need to tell stories with our data? As we've seen before, storytelling helps to communicate and not just inform our audience, our numbers to our audience. But here are some of other fun facts about storytelling with your data. The first one that I put in place is that stories form a unique connection between the storyteller and the listener. When you tell stories, you engage more of your brain and the brain of your audience. And that creates some connections such that the mind of the storyteller and the audience mirror similar brain activity, which we do see here when we are communicating and not just informing. Okay, so the next thing is that stories increase our attention and our empathy. So it helps increase the empathy and the desire for people to act when you are telling them stories rather than just informing them. And that communicates to them and not just inform them. And then stories makes us less skeptical and more open to change. We are able to, we get to understand what is happening, and then we are able to empathize with what is going on. We tend to have it at the back of our minds that we want to do something to change what is happening. And then lastly, stories enhance our comprehension. When you tell stories, you allow your audience to better comprehend difficult or complex concepts. So now the question is, how does data storytelling work? So we want to tell stories with our data. How does these work? How does this process work? So data storytelling involves the skillful combination of three key elements. That's the data, the narrative, and its visuals. And in data storytelling, these three key elements, which I just mentioned, complement each other in different ways. Okay, so first, they help explain, they help enlighten, and they help engage your audience. So with how do they help explain to your audience? This happens when you combine narrative and data. So when you couple them together, it helps to explain to your audience what is happening in the data and why a particular insight is important. And the next one is it enlightens. This happens when you apply visuals to data. You are able to tell your audience what is happening, and you could relate to that if you've been doing some data analysis. You could relate to the fact that sometimes there are some outliers or some patterns that is happening in your data sets which you wouldn't have seen otherwise if you were just looking at your data. But once you plot it or you visualize it, that helps for your audience or for you yourself to be able to relate to it and see what are some patterns that is happening in the data set and what model would best fit your data in that situation. And then lastly, it also engage. And this happens when we merge narrative and visuals. And this is so good. So you don't just visualize your data, but you also narrate what is happening in your data. And these kind of helps engage your audience as to what you are trying to tell them. Okay, so essentially with what we just said, you could see that data story is just a form of persuasion. You are just trying to persuade your audience to be able to do what you want them to do. Like you are trying to let the data talk to them in order for them to drive change or do something else. So in order for that to happen, you need to have a skillful blend of all those three elements that we spoke about. That is narrative, visuals, and data. You need your data, you need to explain what is happening in the data, and you need to visualize it. When you have a skillful blend of all these three, this influences people to drive change and help them and make them want to act. Okay, so now that we know what data storytelling is and what it does and how it could help us, we now consider the science and art of data analysis. And for the science of data analysis, we will consider the foundation and defining a narrative model for data stories. So as I said earlier, with those three key elements that we saw, for data storytelling, the first thing that we need is to obtain our data. That's the first thing that we need to do. So if you want to do like a data storytelling, that's the first thing that you need to get. You need to obtain your data, because you can't do a data storytelling without a data. So how do we obtain data? There are two ways that we could obtain data. We could either obtain it from a primary data source or a secondary data source. So from the primary data source, this is like a first-hand data gathered by the researcher himself, and it is mostly designed for solving the research problem at hand. So you have some research problem that you want to solve. So whatever variables that you need to solve this research problem, you have it at hand. So you try to create like a survey, an interview, or an experiment in order for to disseminate to people, for them to answer these surveys or interviews or do whatever experiment that you want in order to answer that specific problem at hand. So here you get all the variables that you need in order to solve that problem. And then whereas in the secondary data source, mostly we get it from databases. And here are some free databases that you could get data from to help you with your analysis, and that I've listed here. We do have the National Health and Nutrition Examination Service, which is popularly known as NHANES. that it, and this survey is still ongoing. They are still keeping tabs on it, and they are still collecting data as of now. So it's good and it's free. You could use it for any medical analysis that you want. And then there's also the MIMIC, which is the Medical Information Map of Intensive Care. There is the UCI machine learning repository, which I think most of us have used if you are doing like some machine learning, you are taking some machine learning classes, and at the end of the class, you need to like have a presentation or a data analysis or whatever at the end of the class. These are mostly places that you could take your data set, which I know most of us are aware of. And then there's the cargo data set as well, and there's the data and story library that's as well that you could get data from. All these data, like I said, are free that you could get data from. You need not to pay to get them. So one thing that I should mention about a secondary data source is that unlike the primary data source, where I said you could get, because it's designed for solving the research problem at hand, and you're able to get all your variables. In the secondary data source, you probably might not be able to get your variables, and this problem happens when, say, you want to do like a causal inference. Your research question is about a causal effects problem, and you want to do this causal inference. So here you might want to adjust for all those variables, all those confounding variables that you could think of that could influence the effects that you are seeing. But in the secondary data set, because it wasn't collected purposely for that research problem, you might not be able to have that variable that you want to adjust for, and that could be a limitation in your manuscript or your study if you are doing one. But the primary data set doesn't have any blame on its own as well. It's kind of expensive, even though you get all your variables and stuff, it's kind of expensive and time consuming. So you could balance between those two, whichever one that you want, and if you could live with the limitations. So once we've obtained our data, the very important thing that we need to take care of is to know what our research setting is. That is, do we want to do like a descriptive analysis? Do we want to do a univariate or associational analysis with inference to a target population? Do we want to do a predictive analytics or a causal inference, which we will talk about as we move on. So with a descriptive analysis, if you want to do a descriptive analysis, not even with a descriptive analysis, with all of those research settings that I mentioned, all those 4 research settings that I mentioned, if you want to do any analysis based on that, you need to get like a tidied and structured data. But in real life, like most of us have noticed, if you keep on doing data analysis, you realize that the data sets that we get are not structured and they are not tidied, mostly because they have some missing values, because they have some out of range or implausible values that you could look at, and because they probably have some implausible combination of values. So when I say they have out of range or otherwise implausible values, what I'm trying to say is, like, sometimes we think it might not just be an outlier. It could be an outlier. Sometimes it might not just be an outlier. That could just be an outrageous number. So I was working on this data set, and I was looking at a range of BMI values, and there was like a BMI value of like 600. And looking at this, I realized, okay, this is not like a plausible value for BMI. So we had to just go back into the database, get whoever pulled up the data for us, and then they checked it, and they realized there was a mistake in the calculation of BMI. So they fixed it, and then we got another data set. So sometimes these are things that arises when you are doing data analysis, and you need to get your data sets clean. Another thing that you could look at, which is mostly the problem of data not being clean, is having missing data. So when you have missing data and you're trying to report your results to, say, your PI or your supervisor or a research team, whoever you're trying to pass this information to, you should summarize the numbers of the missing observation in a footnote, or actually if there's like a huge data missing pattern, you could also show it in an actual table and not just a footnote as well. And then once you've summarized this and you've spoken to them about it, and you want to know, okay, so I have this missing data, what do I do with it? one thing that you could do would be some imputations that you could do to have. One thing that you could do would be to have some imputations for your data. And these imputations that you could do would be looking at the pattern of missingness. You can't just do an imputation, you need to look at the pattern of missingness of your data. So you kind of look at it and say, oh, is it missing completely at random? So does it mean this missingness that is happening, does it have anything to do with other variables in my data set? If it doesn't have anything to do with the variables in the data set, and every participant who has any missingness, other participants has the same probability of having that same missingness, you're good to go. You could just do like a deletion and use your complete data set if you are working with that. And that is if you do have like less than 10% of your data set, your observations missing, and you have enough sample size, you could do like a deletion and use a complete data set. If not, and you don't want to do like a deletion, you could fill out the missing values with a mean or median if you have a continuous variable. And if you have like a categorical variable, you could fill it up with a mode. And some classical methods that people also want to do, and with that, people are not interested in like the mean or the median or something. And if you think you're missing completely at random, it's an assumption that you don't want to, like, it's a strong assumption for you. You don't know, but you know that the variable, that particular variable or that observation being missing is dependent on other variables that you have. Then you could do that is missing at random. You could do like a minus imputation, which increases the randomness in your data set. So multiple imputation. And this is done with minus package in R and the prog MI. If you are a SAS user and you want to do missing data, you want to impute your missing data, you could do it with a prog MI. And if you are an R user, there is the minus package, which is popularly used for this this imputation. And once you do like a multiple imputation, you should know that it's not just the normal summaries that you have. Once you are doing a multiple imputation, you're having multiple data sets. So you need a way to combine those results into one. So there is also the pool function that goes with the minus package that combines that result for you. And there's also the prog MI analyze that goes with the prog MI proc statements that would help you pull up the data set. And I think they both use the Rubin's rule to pull up this data set. There is more on this. If there are more on this online and stuff, if you need more to learn more about missing data. So another thing that I wanted to mention is that you also have to identify, for data cleaning, is that you have to identify implausible combinations of data values. So with the implausible combination of data values, you could look at so say you are looking at a column of gender. Are there some ethnicity values that have been recorded for someone instead of the person's gender or something? You could look at that and try to find out what is happening in the data set. I spoke much about the missing data because that is something that we encounter every now and then. And this is something that is ongoing. These are like fresh things that people are looking at even in randomized trials and stuff. We still have missingness and people are looking at that. So this is like a fresh thing, and that's something that is of importance, and that's why I stress more on the missing data. So so with the descriptive statistics, once you have done your data cleaning and you think you need descriptive statistics is not your end goal, but you want to also do some later analysis. Within the descriptive statistics, you need to test some statistical assumptions as well. If you are looking at a univariate data, you need to identify outliers, some skewness, and then make some transformation. That is, if you have like a highly right-skewed data, you need to do like a log transformation to get it in shape, to get it normally distributed, as that is one of the assumptions with our classical regression analysis that we mostly use for analysis. And then the sample, we need to look at small sample sizes in particular categories, and then try to see if it's small enough, do we want to combine some categories into one, make some of the variables binary or something. You need to get all those together in the descriptive analysis. If you are looking at a multivariate analysis as well, you need to identify multicollinearity in your data set. What I mean by this is you need to identify whether some of these variables, these predictor variables, are very correlated with each other. So you could do this by looking at your VIFs, that's your variance inflation factor, greater than 4 or 5. And then you could see if this is what is happening, you need to take care of it. And then you could look at redundant variables. So once you have like two variables being so related to each other, one of them could be redundant. You could take one of them out. But which one to take out, you might not have any idea. So maybe some classical methods in your later analysis could help you take out these redundant variables. Okay, so once you've done these data cleaning, you've done these assumptions, you've checked these assumptions and stuff, the descriptive analysis is mostly about characterizing the study sample. And this is mostly shown in table 1 in most manuscripts, in most medical data analysis and manuscripts that we've done. It's mostly shown in table 1, and I'll show you an example of what a table 1 looks like. And it also gives a more in-depth understanding of the data. Your table 1, which is what you've done for your descriptive statistics, also gives like a more in-depth understanding of the data. So doing a descriptive statistics does not require any formal probability modeling, and we'll talk about that later. Okay, so like I said, I was going to show you an example of what a table 1 looks like. So this is like a publication ready table 1, which was in one of our manuscripts. So this table, in this table, one thing that you could recognize from this table is that you should have the heading of the table, and then like I said, you are trying to characterize what the data sample is about in your table 1. So if you have like a continuous variable, you could give the mean and plus or minus the standard deviation. And if that continuous variable is like very, very skewed, you could give like the median and the interquartile range for that instead, and not the mean and standard deviation, because they are not robust to outliers. And then we could also, so for continuous variables, categorical variables, sorry, you just have to get your sample size and the percentage of it in your data set. So you could use that to determine whether there are smaller categories in your data set as well. And then we could see that we have like one line binary. This is what some manuscripts or some journals want. They just want you to report one line for every binary variable. So you realize that here we have like a female sex, and we don't have like the male sex recorded here. You should know that if I have 762 female sex and I have a total of 2,202 observations, which is the N written up here, then you should know what the percentage, the value is for the male sex. And then if you have like a 34.6% of them being females, then what is the percentage of men? For males. So they don't allow you to include both binary levels in your data, in your table 1, in order to save space. And one more thing that I wanted to talk about is that when you have your table 1, you should know that everything about this table should be included in the table. Someone reading your study or reading your manuscript shouldn't have to go back into your manuscript to be able to understand what is happening in this table. So you realize that here, whatever they want to explain is being done. You have to like get some character for it and use that and explain that in the footnote here. So here we have this sign, and then that tells us that the albumin to creatinine ratio was calculated with albumin measured in milligrams and creatinine measured in grams. So someone might want to know, okay, what's the measurement of albumin to creatinine ratio? So you need to tell them what is happening in there, and that's all that goes into the table 1. You need to let them know what is happening. They don't have to go back to know what the measurement is supposed to be. Okay, so the next on our list is the univariate or associational analysis with inference to a target population. So here we have like a sample size, we have like a target population. This is our population. But we can't get to the entire population. So we need a sample, and that's what statistics is all about. If you are able to get to the entire population, some of us will be out of jobs by now, because there will be no need to do like statistics. So there will be no need to take samples. But fortunately for us, you can't get to the entire population. So you need a sample. So you need us to be able to get those estimates for you. So you take a sample and you want to make that inference to that target population. So what you want to do is sometimes to determine some characteristics of that target population. And some example would be, you want to determine what's the incidence or the prevalence of some disease. I mostly do use disease and stuff for, I'm using that because I'm like a biostats person. So pardon me if you need some economics languages and I'm not using that. Okay, so or you want to look at some distributions, that is the mean, the median, or the quantiles, etc., of some health outcomes such as the duration of a survival, the quality of life, or some functional status of the patient. So this, you could do that with a univariate or associational analysis. Or you also want to look at some relationships between an outcome and one or more predictor variables, whilst adjusting for other factors. Here, when I say adjusting for other factors, you are just adjusting for factors that you could get to adjust for. Because it's not a causal question, you are okay, you get to go away scot-free for not adjusting all the variables. You are just trying to go above and beyond. You don't need to adjust for variables in order to show that associational analysis or associational results, but you want to go above and beyond. So you want to adjust for those factors because you have them. So here the goal is usually to provide insight into some disease process. Again, like I said, still using diseases, and not some evaluation of causal effects, which we will look at later. And then our goal is here to do that. We can address this by some regression analysis with focus on estimates that characterizes the relationship between the outcome and the individual predictor variables. Here, to build that regression analysis, we need some probability model relating the result to the population result. The sample results to the population results. So in this, what I mean by the probability model is you need to know what is the probability distribution of your outcome variable. Is my outcome between the values of 0, 1? Oh, okay, then I need a beta regression. You go for that. Is my outcome kind of like right skewed? Do I need to like do some log transformation and use the regular linear regression? Do I want to go for a gamma regression? All those are stuffs that you need to get. So you need to know the probability distribution of that in order to be able to know what model to build in order to answer that question that you have. Okay, so the next on our list is the predictive analytics. So looking at the predictive analytics, we want to build predictive models for occurrence of a particular event. So one of it is we want to build like a risk prediction model for clinical decision support to help the doctors or to help make some clinical decision support in that situation. Or you want to be doing like you want to be predicting individualized treatment effects, and that's mostly dealt with in precision medicine or personalized medication regime. So that's what we call it. So here, what we are trying to do is, I'm trying to predict if this person is going to take like a normal dose of this drug, is this person going to take like a double dose of this drug, or is he going to take like half of it, or do that person need an alternative drug for that same illness that they have. So this is what a predictive analytics does. And then this is mostly addressed by regression and classification model. But the goal of prediction is not describing association. We don't want to do what we were doing before. We don't want to look at what's the association between this and that. We just want to do what do we get at the end. And association with specific predictor variables, like I was saying. So these like regression analysis that we look at, mostly before we used to do like a linear regression or like a logistic regression for this, but now there've been more techniques, more machine learning techniques developing, which you could use to build a better prediction model. And some of them are the random forest model, the decision trees, neural networks, boosting, and other tree-based methods that you could use. And this can be done with or without a probability model. Using these machine learning techniques, you don't need a probability model. But when you are doing like a logistic regression, you need to have a model that is the binomial model in order to be able to do that. So you could do it with or without a probability model, and that's okay. Here is just a figure showing what a predictive analytics is all about. So here you have like a baseline demographics and socioeconomics status, some billing claims, and some real life clinical data about the person. And then you put that into this rate building machine, which we were talking about with the machine learning techniques. Some ensemble methods, some decision tree methods, some boosting, and then some survival methods. It goes through in here into this black box, and then it spits out what's the patient's risk score at the end of that. And these are the predictions that we are interested in. We are mostly not interested in what is going on here, but we are interested in what gets out at the end. Okay, so last on our list is addressing this addressing a causal inference problem. And I think I will relate to this meme here, which I think most of us had seen already. And it's about this lady and this, I think this is a guy, and they were talking, and he was like, I used to think correlation implied causation. And then I took a statistics class. Now I don't. Okay, sounds like the class helped. Yeah, that class helped me, because I also used to think association was causation until I took a statistics class, which I'm supposed to take. And now, well, maybe that helped him, but for me, that helped me as well. So with a causal inference question, the question is, it wants to address what is the effect of applying some intervention or applying some exposure on an outcome Y. And this is it. We have some exposure Y and exposure X, and we want to know what's the influence on Y. And in order to know this relationship or this effect, an example would be, I want to know what's the effect of smoking on lung cancer. But there could be other variables that could also explain the relationship that is happening between smoking and lung cancer, which we need to adjust for. Because if we want to know the explicit relationship between smoking and lung cancer, it should just be about those variables and not other variables. So in that situation, we need to adjust for every confounder that we have in this situation. And that's this C right here. It's just a variable associated with the X and the Y variable. So an example could be, we have like alcohol use. So people using alcohol, more people using alcohol would have a higher, smokers would have a higher chance of also being alcoholics. So in that situation, we are seeing a high rate of lung cancer, because alcohol is related to both the lung cancer and also the smoking status as well. So what we want to do is to make the distribution of alcohol drinkers the same in smoking. So for smokers, you want to know that the percentage or the distribution of alcohol drinking in smoking is the same as for people who do not smoke. And then we are able to look at that relationship. So we need to gather all those variables that could influence this relationship and adjust for them in order to make a causal inference. So if you don't do that and your goal is causal inference, I bet you if you write your results in an article or your manuscript, you would always have queries. You would always have like feedbacks coming back to you saying, this is not a causal interpretation. So you should take that causal interpretation out. There's been more methods to help with causal inference, but it's mostly addressed by using regression or some propensity score model. But where the goal here is to estimate the difference of the outcome in the treatment or exposure group versus the people without the treatment or the exposure group, whilst adjusting for all those variables. One other way to all this that I was talking about is based on you having an observational study. What we know before is that to have like a causal inference question, you need to do you need to actually do a randomized experiment to be able to have a causal inference. But no, you could also have a causal inference question answer in an observational study, provided you are able to adjust for all those variables. There are some questions that you can't even answer with a randomized experiment. Like the example that I gave, you can't randomly assign people to smoking and people not smoking. That is not ethical to do. You wouldn't even get an IRB approval for that kind of analysis. So you don't have to. So you need an observational data in order to do this analysis, and that helps if you're able to adjust for all the confounders. Here, we also need both a probability model to relate the sample results to the study population and a framework to be able to make this causal inference interpretations. Like I said, you could build like a propensity score model, which helps cater for these assumptions of causal inference. Okay, so I think we are done with the science of data analysis. Now we move on to the art of data analysis, and we do this with some statistical graphics and visuals and the do's and don'ts. So here is also another quote from Stephen Few, a data visualization expert. He said that when we have numbers that have an important story to tell, but they do rely on us to give them a convincing voice. Mostly this is done by giving them some graphics and visuals that is like cutting edge, that is going to help people get that. And Tufte, in his paper, data visualization paper in 1983, which helps a lot because it gives me some do's and don'ts about what to do in your your statistical graphics and visualization. It tells us that even though we are trying to show convincing voice of the data, it requires us telling the truth about the data and not just saying what is something else to the audience. Okay, so what do we mean? Here are some guidelines for statistical graphics. What he says, Tufte, in his 1983 paper that I mentioned before, says that it seeks to drive a fair balance between two errors. And that is one, avoid obvious distortions by extreme axis truncation. And that is what is shown in this figure in the left-hand panel to my left. Here we realize that it doesn't start from zero. I think it starts from somewhere around 35,000, and then it goes to 40,000, and then it goes to 45,000. So if this was a zero, it is truncating it all the way to 35,000 and shifting all the way to 40,000. So in here, we see like a steep increase happening as the years increases for first year enrollment. And then we have like this sharp decline right here, which is what is telling someone. So when you look at this, you see, oh, okay, there is like a steep increase happening here. But when you look at the right-hand side, this doesn't show that steep increase. It's just a steady increase that is happening here. And then we have like a decline. It's so a sharp decline, but it's not telling us something different as what this graph is trying to tell us here. And then the next thing that we need to avoid is that we need to avoid contracting the visual information into small portions of the graph. So in my right-hand panel here, even though this is the right figure that we are showing, you could see that this figure is just up there, and it's not, all the down part of the graph is not being utilized. So that is what this person was trying to do by truncating the results in this graph. And this person was trying to show the right results in this graph, but here it's just up there, trying to get this the figure on the graph to cater for everything on the graph. But here you realize that you truncate it enough so much that it tells something different to the audience. So what you could have done would be to just do 0 to say 30,000 or 35,000, and then you move on to 30,000, and then you move on to 60,000, and then so forth. So once you have that and you cap the limits of your visualization to at just that value. So say it goes all the way to say 55,000 or so, and you cap the limit at 60,000. That's it. It will stretch the value. It will stretch it out, and it won't truncate the axis in order to distort the message that you are trying to pass. Okay, so another thing that we should notice is we should give an important, it's important to plot the most informative and most relevant summary measures and to avoid distortions due to oversimplification. So here is also another example to explain that point. Here they were looking at, is democracy good or not? So here they were looking at, here in the left-hand panel, they were looking at percentage of people who say it is essential to live in a democracy and over the years. So in 1930s in Sweden, they went and then they asked you, so if you are one of the participants, they ask you, do you think democracy, do you want to live in democracy? Is it essential to live in democracy? You either say a yes or a no. And then you keep it that way. But mind you, there could be people who thinks democracy is okay, but they could be somewhere in the middle. Say so what you want to do is to give them like a scale and ask them, on a scale of 1 to 10, do you think it's essential to live in a democracy? Now they have something to choose. If they don't want democracy at all, they would choose 0 for sure. If they do want it, but in some part of it, they could choose a 4, a 5, or a 6. So you get to let them be able to choose within the middle and not just give them like a yes or no. And that's what is happening in this graph. So you could see that asking that kind of question, this in Sweden, you could see like this sharp decrease, this steady decrease, this steep decrease for Sweden. In the right-hand panel, where they asked what's the average importance of democracy on a scale of 1 to 10, and people were choosing. Look at what happened with Sweden. It's up there, even above 9, a point of 9 for average, and it's not having that steep decrease as the years increases. So we should be able to strive to get the right summaries in order to convey our message, and not just whatever summary comes to mind. That's what we want to do. Okay. So next, the question at what we want to look at is like some alternative versions of junk. We are looking at these 2 life expectancy table, and this is also what Tufte tells us in his paper. And it says to avoid unnecessary high data ratio. So these 2 graphs are actually saying the same thing. This the bar chart is saying the same thing as this dot plot or this scatter plot is saying. But here you could realize that there is much ink in the right-hand panel as compared to the left-hand panel. And this is both saying the same thing. Looking at these 2 graphs, you will be able to get the same results out of this. But one thing too that you could notice is in the left-hand panel with this dot plots that we have, we could also include like error bars around the dot plot to be able to show what the confidence bands is. Asia is Asia showing results that could also be in Africa. So it doesn't, you could just show something else other than this point estimate of means and show the confidence bands as well. When you show a confidence band in this right-hand panel, that would not suffice. You wouldn't see anything with this bar graph by showing the error bars with this. And then some other guidelines that we should look at is, we're getting very close to the end, that I want to leave you with is that we want to respect the level of measurement in the data. So if we have like an ordered categorical variable, we should use ordered colorization palettes to do that. So if you have like a low, medium, high, you should be able to show some ordered colorizations to do that. So from light to dark, so from light blue all the way all the way to like dark blue, or from green to red, like some colors that show some colorization palette. You should use that. And when you have like a nominal scale variable, don't bother doing any colorization, ordered colorization palettes, because it kind of tells the audience something which you don't want them to know. Once you start doing that ordered colorization palettes, they tend to think that your data is ordered, but your data is not ordered. So you just want to do like an ordered colorization, or you could color them all right, but don't make them an ordered colorization. And then you should respect the limit of human perception. So what I mean by this is you should avoid graphs that are too complex to understand. So you should avoid, to do this, you should avoid too many different types of plot or symbols or colors. Color them, but avoid too many of them. Colors that does not make sense, just don't include them. And then avoid too many dimensions on the same plot. So you are creating that plot so you understand what is happening, but someone else trying to understand that plot could take a whole lot of time to understand that plot. You don't want that person to take a whole lot of time to understand your plot. They will just do away with your plot. So try to understand human perception and the way humans would be able to get it. Not just for you. You would understand it, but someone else might not be able to understand it. And then you should pay very close attention to Titles, axes, and labels, legends, footnotes of the graph. Like I said with the table one, even with the graph as well, you should be able to contain all the information with it in your graph. They don't have to scroll back into your manuscript to be able to get what is happening in your graph. So all of the information that you need to be able to understand the graph should be contained on the graph itself. They don't have to scroll back and forth. And these are things that we kind of miss and we need to get. And one thing that I've realized that I personally kind of miss is to include the units of measurement. So if you're plotting, you should always be able to include your units of measurement. If you're plotting age, say, is it age in years? Is it age in months? Is it age in days? You need to include what your unit of measurement is for the people to understand. And then lastly, one thing that I want to leave us with in conclusion for the statistical graphs is that we should pay attention to warnings that we might be falling into data decoration. Yes, we want our graphs to be nice. We want to decorate it enough, but don't fall into that trap. And here are some three things that you could notice. If you are doing these three things, then you probably are falling into the data decoration problem, and you should take care of that. So one of it is if you don't have a clear focus or emphasis on the visuals you are trying to create. So you are trying to create a figure, but you are trying to get, okay, the end will justify the means. You shouldn't do that. You should know what you want the end product to be, and you try to get that visual to look as how you want it to look like. So maybe you should probably get like a statistical analysis plan and get like a mock-up visuals of how it's supposed to look like, and then you can plot it as how you want it to look like. And then secondly, you are more focused on the data visualization tool than the actual data. So you are more focused on what data visualization tool could make me decorate this figure enough, and you are not focused on what the data is actually saying. So maybe you think, I'm not good at using ggplot in R, but I'm good at using like a base R plot to plot my data. But ggplot could say more than what a base R plot would do. But you don't need that. You should be able to just look at what the data wants to say and then try to say it with whatever the data visualization tool you have. You don't necessarily need like a cutting edge data visualization tool to do your work. And then you want to visualize. One thing that we should notice is that once you are trying to create your visuals, you are trying to visualize the data to other people with more domain experts that can make better sense of the numbers. No, you are trying to visualize the data to everyone. So you should be able to visualize the data for me to be able to understand what you are trying to show. Even if I have no idea about how data visualization works, or I don't have any domain experts, I should be able to understand what is happening. So this is all that I have for the art of data analysis, and some references here that I wanted to share with you. If you want to know more about effective data storytelling, you could use Dyke's book on effective data storytelling, how to drive change with data narratives and visuals. And then if you want to know more about what the do's and don'ts of data visualization, you could also read Tufte's paper in 1953, his paper in 1953. And then here, what I wanted to say lastly is that if you are in need of someone to share, like to give these kinds of presentation or tutorials or training on a topic or any data analysis topic to your team, we at Mogital Analytics are available to do that. If you have a data analysis that you want taken care of, we at Mogital Analytics are able to do that for you. But also, I just wanted to leave you with some data management tools that you could look at. So here are some sites that you could use for data analysis in R. I'm an R person, not a SAS person, so I apologize to the SAS people if I don't have any link here for you. But here are some links to some data management in R that you could use. And Tidyverse, I want to mention, it's a good tool for data manipulation and data management. So this link would help you a lot if you are much into data management. Okay, thank you. And if you have any questions, I will be here to answer them. Thank you.
Thank you, Linda. Thank you so much. So time for questions, please. So if you have any question, you can simply unmute yourself and then you can ask your question.